In March 2026, the south vent of Kilauea erupted with violent force. Fountains of molten rock and raw volcanic gas shot almost 2,000 feet into the atmosphere, creating a towering column of toxic material over the island. Managing the fallout from an event like this falls under Section 202 of the Stafford Act. This federal law requires the United States Geological Survey to provide timely and effective disaster warnings to protect the public and minimize economic loss. Yet during the most intense days of the eruption, March 11th through the 13th, the official USGS air quality dashboard for the town of Volcano displayed a perfect green rating. The official public designation was good. Internally, the agency's own Volcano Watch reports documented a radically different environment. Those internal logs recorded continuous fallout of tephra, abrasive microglass, accumulating up to 7 inches deep across populated areas like Volcano Village and the local golf course. Residents living in those impact zones, including individuals with heart stents and severe respiratory issues, relied on the green dashboard as a definitive medical clearance to go outside. They inhaled particulate glass and sulfuric acid mist under the assumption the air was safe. This discrepancy between the dashboard and the fallout suggests a structural failure in the monitoring architecture rather than a simple software glitch. Providing a green safety rating while a community is buried under hazardous material creates a safety signal that contradicts the physical hazards on the ground. The clearest proof of this contradiction sits at the Kilauea military camp, a facility located directly in the path of the March plume. During the exact time frame the air was designated as safe, the atmosphere was heavily laden with corrosive agents. The chemical fallout actively stripped the industrial paint off federal buildings and private homes throughout the camp. If the atmospheric chemistry is acidic enough to dissolve industrial paint on contact, a monitoring system reporting that same air as good is failing to account for physical reality. This oversight directly impacts the Stafford Act mandate to help residents minimize economic disruption and property loss. The first mechanical failure stems from geography. The current network of air quality sensors relies on intake valves that sample ambient air strictly at head height. This 3D map plots the elevation of the volcano region and its sensor nodes against the vertical trajectory of the March eruption. The initial fountaining pushed the toxic plume far above the sensor network, reaching elevations between 15 and 30,000 feet. Caught in high-altitude crosswinds, that massive volume of toxic material sailed horizontally across the region, passing over the designated airspace of the ground-level monitoring nodes. As the atmospheric conditions shifted and the air cooled, the dense mass rapidly lost altitude. The entire toxic cloud dropped out of the sky directly onto the residential grids. Minutes before the drop, the sensors accurately reported clean air at the surface. Moments later, the community was entirely inundated by the hazard from above. Relying exclusively on a flat, two-dimensional ground monitoring network leaves the system defenseless against a three-dimensional, high-altitude hazard transport. The second failure occurs at the chemical level. The standard USGS monitoring equipment is calibrated specifically to target sulfur dioxide, or SO2, in its gaseous state. The town of Volcano sits in a unique microclimate characterized by heavy natural mist, frequent rain, and high ambient atmospheric moisture. When raw SO2 gas enters this environment, it immediately collides with the local water vapor. This triggers a rapid phase shift. The gas bonds with the water and transforms into a liquid aerosol, creating an aqueous sulfuric acid fog. This new liquid aerosol carries immense physical weight compared to a buoyant gas, altering how it travels through the air and settling onto surfaces. Gas-calibrated intake valves physically cannot detect or process liquid acid droplets. As the corrosive liquid bypasses the internal sensors, the public reading remains green. While the machine registers zero gas, human lungs are forced to process the heavy aerosolized sulfuric acid mist, which attacks respiratory tissue on contact. A resident can be standing outside, experiencing acute respiratory distress from acid inhalation, while the dashboard in their hand confirms the air is perfectly safe. Excluding the local environmental chemistry allows the public safety dashboard to broadcast a good rating while the air itself is hazardous. The final mechanism hiding these hazards is mathematical. To determine whether a region gets a green rating, the software relies on a 15-minute rolling average. This chart tracks atmospheric toxicity over a standard 15-minute window. Consider a scenario where an intense pocket of acid mist blows through the area, causing a massive data spike into the red hazard zone for 5 consecutive minutes. Volcanic microclimates are highly volatile. A quick shift in the wind can push that toxic cloud out of the area, and the hazard reading drops to absolute zero, registering completely clean air for the remaining 10 minutes. Before the public ever sees this data, the software averages the sharp toxic spike and the 10 minutes of clean air together. The result is a single flat, low-level green line spanning the full 15 minutes. The mathematics successfully dilute the data, but human lungs do not average out acute corrosive damage over a quarter of an hour. The physical injury from those first 5 minutes is immediate. Temporal averaging masks peak lethality. A green average over a 15-minute window does not guarantee the air is safe to breathe in the present moment. The USGS operates on a research-first, safety-second model. The agency possesses world-class capabilities in geological data collection. They accurately map magma chambers and record the exact physical mechanics of an active eruption. While they successfully measure how the volcano works, they fail to communicate how that eruption physically harms the surrounding population. Prioritizing geological observation over actionable public health alerts is a direct violation of the Stafford Act's mandate to minimize real-world harm. To meet the legal standard of an effective warning system, the agency must deploy vertical profiling. This requires utilizing drones and LiDAR technology to scan the high-altitude vertical column directly above the standard ground notes. Scanning the airspace vertically allows monitoring agencies to detect dense toxic masses and warn communities about falling plumes before they drop to the surface. Policy must also be updated. The agency needs to issue distinct acid mist alerts that are decoupled from the rigid limitations of ground-level gas meters. This requires the official reclassification of tephra fallout as an actionable public health emergency. A truly effective dashboard requires distinct, hazard-specific toggles for actual threats, like microglass and acid aerosol, bypassing generic, mathematically average scores entirely. The ultimate test of the system's validity lies in the physical evidence at the Kilauea military camp. If the agency continues to claim the air was clean during the March eruption, they must explain the chemical destruction of the surrounding infrastructure. Until the monitoring architecture is forced to align with the physical chemistry of the fallout, the USGS will continue to fail its legal mandate, and the public will remain unprotected.